AI needs power. The chip war. Artificial intelligence has become one of the most important technologies of the modern era. Large language models, image generators, recommendation engines, and advanced robotics all rely on increasingly complex machine learning systems. But behind every breakthrough in artificial intelligence lies something less visible: computational power. Training modern AI models requires enormous amounts of processing capability. Massive datasets must be analyzed, patterns must be identified, and billions of mathematical operations must be performed repeatedly during the training process. This level of computation is far beyond what traditional processors were designed to handle. As a result, a new category of hardware has emerged as the foundation of modern artificial intelligence: graphics processing units. Originally designed for video games and computer graphics, GPUs have become the engines powering the AI revolution. And today, the race to build the most powerful AI chips has become one of the most intense competitions in the global technology industry. To understand how this competition began, it is important to look at how GPUs evolved from graphics hardware into artificial intelligence accelerators. Traditional computer processors, known as central processing units or CPUs, are designed to handle many different types of tasks. They are extremely flexible and capable of executing complex instructions sequentially. However, this flexibility comes with limitations when performing highly repetitive calculations. Machine learning workloads often involve executing the same mathematical operations millions or even billions of times. These operations are known as matrix multiplications. GPUs are particularly well suited for these tasks because they contain thousands of smaller processing cores that can operate in parallel. Instead of processing one instruction at a time, GPUs can perform many calculations simultaneously. This parallel architecture allows them to accelerate the types of computations required by machine learning algorithms. In the early 2010s, researchers began experimenting with using GPUs to train neural networks. They discovered that GPUs could dramatically reduce the time required to train complex models. Tasks that once required weeks of computation on CPUs could sometimes be completed in days using GPUs. This discovery marked a turning point in the development of modern artificial intelligence. Suddenly, larger models became possible. Datasets could grow. Algorithms could become more sophisticated. And as these models improved, demand for GPU computing power began to increase rapidly. One company in particular became central to this transformation: Nvidia. Founded in the 1990s as a graphics hardware company, Nvidia initially focused on building GPUs for video games. But over time, the company began investing heavily in parallel computing technologies. One of the most important developments was a software platform called CUDA. CUDA allowed developers to program GPUs for general computing tasks beyond graphics. With CUDA, researchers could write code that harnessed the parallel processing capabilities of GPUs for scientific computing, data analysis, and eventually machine learning. As artificial intelligence research accelerated, Nvidia GPUs became the preferred hardware platform for training deep learning models. Technology companies, research institutions, and startups all began purchasing large clusters of Nvidia GPUs to power their AI experiments. Soon, entire data centers were being designed specifically to house GPU clusters. These facilities contain thousands of processors working together to train massive neural networks. As the demand for AI computing power grew, other companies entered the race to develop competing hardware. Advanced Micro Devices, commonly known as AMD, began developing GPUs designed for data center workloads. Intel, historically known for its CPUs, invested heavily in AI accelerators and specialized processors. Meanwhile, large technology companies began designing custom chips optimized for artificial intelligence. Google developed its tensor processing units, or TPUs, to accelerate machine learning workloads inside its data centers. Amazon introduced its own AI chips for cloud services. Apple began integrating specialized neural engines into its devices. This shift marked the beginning of what many analysts now describe as the global AI chip race. At stake is not just technological leadership but also economic and geopolitical influence. Artificial intelligence is expected to reshape industries ranging from healthcare and transportation to finance and defense. Countries and companies that control the most advanced computing infrastructure may gain significant strategic advantages. As a result, governments around the world have begun paying close attention to semiconductor supply chains. Advanced chip manufacturing has become one of the most strategically important industries in the global economy. Modern semiconductor fabrication requires extremely complex manufacturing processes involving precision equipment and specialized materials. A single advanced semiconductor factory can cost tens of billions of dollars to build. Only a small number of companies possess the expertise required to manufacture the most advanced chips. One of the most important players in this ecosystem is Taiwan Semiconductor Manufacturing Company, often known as TSMC. TSMC produces chips for many of the world's leading technology companies. The company operates some of the most advanced semiconductor fabrication facilities ever built. These factories use extreme ultraviolet lithography machines capable of etching microscopic circuits onto silicon wafers. The resulting processors contain billions of transistors packed into tiny spaces. Such technology allows chips to perform enormous numbers of calculations every second. As artificial intelligence models continue growing in size and complexity, demand for advanced chips continues rising. Training a single large language model can require thousands of GPUs operating continuously for weeks or months. This level of computation consumes vast amounts of electricity and requires enormous infrastructure investments. Data centers built for AI workloads often contain specialized cooling systems, high-speed networking equipment, and massive power supplies. Inside these facilities, racks of servers filled with GPUs operate together as giant supercomputers. The competition to build faster and more efficient chips has therefore become one of the defining technology races of the 21st century. Companies are investing billions of dollars in research and development to improve chip performance. Architectures are evolving to support new types of machine learning algorithms. Memory systems are being redesigned to move data faster between processors. And specialized accelerators are being developed to handle specific AI workloads more efficiently. At the same time, geopolitical tensions have begun influencing the global semiconductor industry. Export controls, trade restrictions, and national technology policies are shaping how advanced chips are distributed around the world. Governments increasingly view semiconductor manufacturing as critical infrastructure. Some countries are investing heavily in domestic chip production to reduce dependence on foreign suppliers. These developments illustrate how artificial intelligence has become deeply intertwined with global economic and political dynamics. The AI chip war is not just about faster processors. It is about who controls the computational infrastructure that powers the future of technology. Every breakthrough in machine learning ultimately depends on hardware capable of performing the necessary calculations. Without powerful chips, even the most sophisticated algorithms cannot operate. And as artificial intelligence continues advancing, the demand for computational power will likely increase even further. In many ways, the future of artificial intelligence may be shaped as much by semiconductor engineering as by software innovation. Because behind every intelligent system lies a vast network of processors performing billions of calculations every second. And the companies and countries building those processors are engaged in one of the most important technology competitions of our time.